All right, pre-calculus, we are now ready for 3.4 graphs of polynomial functions. Again, a few more reminders. The domain represents the set of all possible input values. So those are generally our x values. And then polynomials, if we're to graph them, they are smooth and continuous. Okay, they're smooth and continuous curves. What this means is there are no holes, skips, jumps, or any sharp corners. Like with an absolute value, that v, there's a sharp corner. With polynomials, we don't have any of that. So for example, this polynomial h of n, where we have the binomial n minus 3 times n minus 5 times n plus 6, has the n-intercepts. Let's put a hyphen in there so you don't think that's the number of intercepts. And it's like saying x-intercepts. So it has the horizontal intercepts at 3, 0, 5, 0, and negative 6, 0. Remember, by setting each of those binomials equal to 0. And then the h-intercepts, or our vertical intercepts, is going to be at 0, 90. So we plug in 0 for our n, and when we multiply what's left on the right-hand side, the negative 3 times the negative 5 times the positive 6, we would get 90. And the zeros, or the roots, remember, are just those x values, or in this case, the n values of negative 6, 3, and 5. We come from there. Let's consider f of x equaling this polynomial, where we have the binomial x minus 2, but then that's being multiplied by the binomial x minus 7, that quantity squared. So technically, 2 of those are showing up. And then we have 3 of the x plus 8. Problem is, we can't have more than one intercept at a single point. So what we say is f of x has zeros at x equals 2 with a multiplicity of 1, meaning it only shows up one time in that equation. X equals 7 with a multiplicity of 2. And x equals negative 8 with a multiplicity of 3. What do we mean when we say multiplicity? It's how many times that 0, or its factor, is in the equation. I use EQN for short for equation. So the x minus 2, that zero's factor only shows up once. The x minus 7, technically there's 2 of those, and then there's 3 of the x plus 8s. Now, how does this help us? Is the multiplicities of the zeros help us figure out the behavior at that x-intercept. Graphs of multiplicity, even multiplicities behave like an x squared, like an even polynomial. Remember, those are parabolas. So they bounce off the x-axis. So an example would be if you had this graph, that 0 has even multiplicity. If it has an odd multiplicity, it behaves like an odd polynomial, like this guy, and they cross through the x-axis. Now, with the odd multiplicity, the higher the multiplicity, the flatter the graph is at the 0. So for example, you might have an x-intercept here and an x-intercept there. So this has an odd multiplicity, could be 1, but this has a higher odd multiplicity. It could be 3. So they're wanting us to sketch the graph of this parabola using our knowledge of zeros and multiplicities. So again, when we say roots, that's the same thing as zeros. So in this case, we have a 0 of 3 with a multiplicity of 1. We have a 0 of a -2 with a multiplicity of 2. And we have a 0 of 5 with a multiplicity of 3. So those are our roots or our zeros. We also want to know the y-intercepts. And I know it says plural there, but really, if it's a function or parabola, we're only going to have one intercept, right? So a y-intercept, that means our x is 0. So if we plugged in 0, here's the little work off to the side. If we plugged in 0, f of 0, we would get a -3 times 2 squared times -5 cubed. And that would give us 1,500 for our y. I know it seems awfully large, but again, we are sketching the graph. The degree, notice there's the multiplicities. We can add all of those up. We have a multiplicity of 1. The second x shows up twice, so that gives us 3 x's. The last 0 shows up 3 times, so 3 more. So this gives us a degree of 6, so we know that it is even. And then the end behavior, notice the leading coefficient is just a 1, a positive 1, and it's an even polynomial. So that means it's going to do this. So as x approaches either positive or negative infinity, the graph is going to go up towards positive infinity. So let's just kind of take a quick sketch of what we think this guy is going to look like. Again, our zeros are at -2, 3, and 5. And our y-intercept is way up here, but it doesn't have to be to scale. Again, we're just sketching it. Our y-intercept is way up there at 1,500. So we know it's of degree 6 and it opens up. So as we're going to this first 0, x equals -2 with a multiplicity of 2. Remember, our multiplicity, if it's even, it's going to bounce. So we know we start upwards. We're going to bounce off of -2. We know it crosses the y at 1,500. We know the multiplicity of 3 is 1. So it's going to cross 3, but not really flat, right? And then 5 has a multiplicity of 3. So it might be a little bit flatter there at 5. I didn't quite hit that. So again, it is a sketch. It is not every single point just exact, but we've got the big pieces. We have the end behavior, we have all of the intercepts, The degrees are correct. So it's just a nice quick sketch of the graph. Now we're asked to find a possible equation for a 5th degree polynomial. So that's important. We know how many x's are going to be multiplied, where we have roots of multiplicity of 2 here and multiplicity 1 here at x equals 2, and then it goes through the point 5, negative 576. So 5th degree polynomial, so we know we have f of x equals some coefficient a. The first root of multiplicity 2 is x equals negative 3, so that would give us an x plus 3 squared, multiplicity of 2. A 0 at 4, so we have x minus 4, again a multiplicity of 2. And then another 0 or root of a multiplicity 1 at x equals 2, so we have x minus 2, technically to the first power. So 2x's times 2x's times 1x would give us x to the 5th, so we do have a 5th degree polynomial. But again, we have to find that a, so we're going to use our point 5, negative 576. So this time they didn't give us the y-intercept, but we can still use that point. So the y value is negative 576. We don't know the a, and our x's are 5. So 5 plus 3 squared, 5 minus 4 squared, 5 minus 2. So 8 squared is 64. 1 squared is 1, 5 minus 2 is 3, equals 192 times a. So that means when we divide by 192, we get a to be a negative 3. So our possible equation for this 5th degree polynomial is negative 3 times x plus 3 squared times x minus 4 squared times x minus 2. Now in that example, they actually gave us the zeros. They listed it in words, and then they gave us another point. We can do the exact same thing if they give us a graph. We need to know the zeros. We need to know their multiplicities. We know this one is even. We know that this one is odd. And odds are this one is going to be a larger odd. And again, how do we know that? We know it has an even multiplicity because it's bouncing off the graph. And it's an odd multiplicity because it's going through the graph. So we can start with f of x equals a. Our first one is negative 3, so that gives us an x plus 3, but we know it's at least even, so we can square it. The next one is odd at negative 1, so x plus 1. Now right there, that gives us only 3 x's, right? But we know the fact that it is opening up in both directions. Look at this end behavior. Not only is our a positive, but our degree is going to be even because it's going in the same direction. And since that 4 is flattened out, more than likely, that guy is a cube instead of to the first power, a little higher exponent. Remember, they're flatter. So now in order to solve this though, we need to find another point that we can plug in and solve for our a. Now, I don't know about you guys, but it would be nice. That looks like a y-intercept there. Use a point that you know what the value is. Don't try to guess too much. So if it goes at a hash mark, use that one. So if we use 0, negative 120, then we would have a negative 120 equals a times 3 squared times 1 times a negative 4 cubed equals a times 9 times 1 times a negative 64 gives us a negative 120 equals a negative 576a. And when we divide and reduce, we would get a positive 5/24. So our final equation, f of x equals a positive 5/24 times x plus 3 squared times x plus 1 times x minus 4 cubed. Now let's do some calculator work. Now, if not all of you have a graphing calculator that you can use, sometimes they have loaners on the campus, but also there's some free apps that you guys can look up. There's Desmos. I can't think of some of the others right now, but we'll post them. So I'm going to switch over to my calculator so you guys can see what that looks like. All right, so they're wanting us to find the solution to the equation 0 equals x cubed minus 5x squared plus 3x plus 1. So to solve that by graphing, you're going to look for the y equals button here underneath the graphing screen. And we're going to type in the right side of that function, but notice it was already equal to 0. Okay, so we have the function x cubed, I'm going to get out of the exponent, minus 5x squared plus 3x plus 1. Now, in order to graph it, we want to be sure that our window is appropriate. If you want to do a negative 10 by 10, we can do a zoom standard. So if you hit the zoom button, go down to zoom standard, hit enter, it will actually graph it for you. Now, we can also zoom in if you wish. You don't have to, but we can hit the zoom button and say, if we look at the graph, we don't need to go all the way out to negative 10 to 10, maybe go out to 1, 2, 3, 4, 5, 6, maybe negative 3 to 6. We can always change the window. We can change the x to a negative 3 and the x max 6. The x scale just says that your hash marks will count as 1, unless you want to do it by 5s or 10s, then you can change the scale. And then the y min, we can go from, let's say, negative 5 to 5. Now, also notice when you're putting in the negative 3s on your graphing calculator, if you're new to the graphing calculator, this button down here next to the enter is your negative symbol. If you use the minus sign, it will show you an error. So be sure that you only use this negative unless it is a subtraction. So then we can hit the graph button and they'll regraph it where notice it's zooming in a little bit. Well, if they're wanting us to solve that equation, that means they want to find out for what values of x are the y values 0, because it was set equal to 0. So that's basically finding our x-intercepts. So notice here above the word trace, there's the word calculate. So we're going to hit our second function trace, and it's going to allow us to get to that calculate. And we want to calculate our zeros. Okay, not minimums or maximums or anything else, just our zeros. So we hit enter, and we have 3 of them. So notice I'm going to hit this arrow button, and it's going to move my cursor there on the graph all the way over to the left, because I first want to find this left 0. So if we go down here, it says left bound. It's wanting us to give an interval where we know that 0 exists. So they know that we're looking for the same 0. So I'm going to move that cursor just to the left, and I'm going to hit enter. And notice it gives me a little marker here. So we know that it's to the right of that. And now I'm going to give the right bound. So I'm going to go to the other side of my 0 and hit enter. And notice it gives me a marker there. They're asking, do you want us to guess or estimate the x-intercept between those 2 markers? And then I'm going to hit enter again to say yes. And then it's estimated a 0. So we would write down a 0 of negative 0.24, because it said to round to 2 decimal places. So negative 0.24 comma 0. So this is one of our solutions. Notice we have 2 more solutions, so we're going to do the same thing. We're going to go back to second function calculate, We want to calculate a 0 again, but this time we want this other 0. So I'm going to go to the left of that 0. So left bound right here, hit enter. So that line needs to be to the left. And then right bound. All right, so we're going to go over here towards the right side. I can make it a little bit wider so you can see. So I've hit the left bound and the right bound. And notice that 0's in between. I hit guess, yes. And it says, hey, look, it landed at 1. So there's another solution. And then you could do the same thing over here. And you guys can try that on the own. And it should give us a 4.24. Okay. So when we are doing these, we found the left one to be a negative 0.24, the second solution to be 1. And if you did that third one on your own, you would got approximately 4.24. And now we have one of our first theorems throughout this semester, and it is a huge one. It's called the intermediate value theorem. We sometimes do a little shorthand, IVT, but that basically says if we have two y values. So let's say if we have f of a and f of b on a polynomial, and their signs are different. Okay, in other words, opposites. One's positive, one's negative. There must be at least 1 0 between A and B. So let's use this graph here again to kind of illustrate what that intermediate value theorem is representing. So f of A and f of B are representing two y values. Okay, so let's suppose I'm looking down here at the y value of f of 3. It's down here somewhere. I don't know the actual value. I can kind of estimate it there, but I do know it's negative. And if I go over to f of 5, that y value is up here somewhere. I'm not exactly sure what it is, but I know that it's positive. Remember, polynomials are continuous. There's no skips, holes, or jumps. So the only way to get from a negative to a positive is to cross that x-axis, is for somewhere the y value to be 0. So that's why you're guaranteed at least 1. There could be more than 1 in between, depends on how big that interval is. Likewise, if we looked at, let's say, down here, the y value at 1 is way down here, and it's negative, and the y value of 2 is negative, well, there's no 0 in between there. If we go over here, let's take a look at -4 would be somewhere up here that's positive. -2 is also positive, but notice there is a 0 in between. So one of the things that I wanted you guys to understand in this theorem is if the signs of the y values change, that means it had to cross the 0 somewhere in between. If they don't change, it doesn't tell us anything. There could be no 0, no x-intercept, like here between the f of 1 and f of 2, or there could have been a 0 in between, like where it bounces off. So it only gives us information if they change signs. If they don't change signs, that doesn't mean there's not a 0. So let's do a quick example. We want to show that this function has at least 1 0 between x equals 1 and x equals 3. So we need to determine what our function values are at 1 and at 3. So if we plug in 1, there's an x cubed, so we get 1 cubed minus 5 times 1 squared plus 3 times 1 plus 6 And that gives us a positive 5. If we plug in the 3, we get 3 cubed minus 5 times 3 squared plus 3 times 3 plus 6. And that gives us a negative 3. So since our y values change signs by the intermediate value theorem, or IVT, there is at least 1 0 between the x values 1 and 3. All right, guys, and for a quick visual there, I'm not going to graph the whole thing, but all we know is that when x was 1, we got a y value of 5. And when x was 3, we got a y value of negative 3. So if it's a continuous function, it has to somewhere cross that x-axis between 1 and 3. All right, I hope you guys enjoyed section 3.4. If you have any questions, don't hesitate to come and see me. Thanks. I'll see you soon. Bye.